Welcome to The Explainer. Today, we're going to pull back the curtain on that magic box you use every single day. We're going to trace the unbelievable journey that happens in the blink of an eye, from a single key press all the way down to the billions of switches that power our world. Think about it for a second. It seems so simple, right? You tap a key, a letter appears on the screen. But that single, simple tap kicks off an absolutely incredible journey, a whole chain reaction of physics and logic that unfolds at pretty much the speed of light. And we're going to trace that entire journey to unravel the mystery. We're going to follow that signal from your finger down, down, down to the billions of microscopic switches that make up the computer's brain, and then all the way back up to the pixels that light up your screen. At a really high level, almost every interaction you have with a computer follows this exact path. It starts as a physical thing you do. It becomes an electrical signal. That signal gets converted into digital binary, ones and zeros. And finally, it gets stored in memory. It's this fundamental transformation from our physical world into the digital one. So, let's start that journey from your finger to the computer's brain. And it all begins right at the keyboard. This is the physical gateway where your actions get translated for the very first time into a language the computer can actually understand. Just look at all the layers of translation going on here. Your physical key press completes an electrical circuit. A little controller chip inside the keyboard detects that and generates a unique number, a scan code. That code then travels as a bunch of binary pulses over to the operating system, which finally looks it up and says, aha, that's the letter A, and then it sticks it into memory. This whole crazy sequence happens in a flash, every single time you type. Okay, so our letter A is now officially data, and it's just sitting there in memory. But so what? Just having it sit there doesn't do much. To actually use it, to do anything with it, we have to go inside the computer's brain, the central processing unit, or the CPU. The best way to think of the CPU is like the master chef in a giant kitchen. It doesn't store the ingredients. That's memory's job. The CPU's whole purpose is to be this unbelievably fast and obedient engine that takes instructions and processes the data, executing billions of commands every single second. And this four-step cycle, this is the fundamental rhythm. It's literally the heartbeat of all computing. It doesn't matter how complicated your software is, it all gets broken down into millions of tiny little instructions that the CPU processes by following this exact loop. Fetch, decode, execute, store. And it does this over and over and over, billions of times a second. So when we get to that execute step, where does the actual work happen? Well, it happens right here in a very specialized part of the CPU called the Arithmetic Logic Unit, or ALU. You can just think of this as a superpowered calculator that handles all the math and all the logical decisions. Now, to work at these mind-boggling speeds, the CPU can't just sit around waiting for data to travel all the way from the main memory, or RAM. Even at the speed of light, that's like a cross-country trip. So it uses these tiny, ultra-fast storage spots located right on the CPU chip itself. They're called registers. They hold the exact piece of data the ALU is working on in that exact moment. But hold on a second. How can a machine made of metal and silicone actually calculate or think about anything? The answer is so much simpler and honestly so much more profound than you might imagine. It all boils down to one simple ultimate building block. And this is it, the transistor. This is the absolute bedrock of all modern computing. It's really nothing more than a tiny, microscopic electronic switch. It has no moving parts. It can just be turned on or off with a little pulse of electricity. And you have literally billions of them in the device you're watching this on right now. And this right here is the brilliant core concept of all computing. By controlling whether a transistor is on or off, we can physically represent the two digits of binary code, 1 and 0. And that's it. Every single piece of information on your computer, every photo, every song, every word, is stored and processed as just a huge sequence of these ones and zeros. So how do you get from a simple on or off switch to something that can process our letter A? Well, you start combining them. By arranging these simple transistors in very specific patterns, we create something called logic gates, which can make really simple decisions, like if switch A and switch B are on, then turn on switch C. Okay, now, let's scale that up. You combine thousands of those simple logic gates, and all of a sudden, you have a circuit that can perform addition or comparison. And just like that, you've built the arithmetic logic unit, the very same superpowered calculator we were just talking about. And then, when you combine that ALU with a control unit to direct all the traffic and those super fast registers for temporary storage, you get the whole shebang, the entire brain of the computer, the CPU. I mean, it's amazing, isn't it? This incredibly complex structure emerges from absolutely nothing but simple on or off switches. So the CPU processes data using its transistors, but where does it get that data from? And where do the results go? Well, it all comes from a really sophisticated, multi-layered hierarchy of memory. The best way to think about it is like a pyramid. It's designed to kind of cheat the laws of physics, because you can't have storage that's both massive and instantaneous. So the computer intelligently shuffles data between these layers, from your slow hard drive to your fast RAM to the even faster cache, all to make sure the CPU always has what it needs right when it needs it. Okay, let's zoom back out now and see how all of these pieces, the transistors, the CPU cycles, the memory pyramid, how they all work together in perfect concert to run a really simple piece of computer code. Even a super simple line of code like C equals A plus B goes through this entire process. The instruction gets loaded into memory, the CPU fetches the command and the data, the ALU performs the calculation on the ones and zeros, and the result is stored back. Every single program you run is just millions and millions of these basic operations, all happening in sequence at an incredible speed. So what this all really means is that the vibrant, interactive world on your screen, at its very core, it's an illusion. It's a really elaborate, beautiful construction built from the simplest possible foundation, just patterns of electricity flowing through logic circuits. And this entire illusion is made possible thanks to the perfectly coordinated effort of billions, that's billions with a B, of these microscopic switches, all firing in perfect harmony, orchestrated by the steady pulse of the computer's internal clock. The whole thing just shows that immense complexity and creativity can emerge from the simplest binary rule there is, on or off, 1 or 0. It's not magic, it's just an incredible, incredible symphony of switches.